Okay. Fair enough. Okay, so just before I start, this tutorial has a lot of content. I sort of would rather adjust it to the audience and the interests of the audience. So I'm curious, who is here just because they've heard this acronym RDDL and they just want to know what the heck it means? Okay, versus, that's A. Okay, because I assume at least you're here for A. Versus B, you actually think you might use riddle. Okay, so who's potentially here for B? Might actually use riddle. B. Okay, and okay. No. I won't be offended. But the next question is, what is it that you think you want to model? So Maria, I'm going to assume hybrid domains. I'm going to assume continuous time, which unfortunately I'm going to disappoint you for. So I think I know Maria. So for you?
For me, generally, RDDL, yeah. Well, yeah.
Oh, okay, but stochastic, continuous, discrete, continuous time, discrete time.
In my case, discrete time.
Okay. Good.
Yeah.
Partially observable, fully observable.
Partial observable.
Yeah.
Partial observable is
Okay. Good. And over here, I know the back way, partially observable, robotics problems. Anyone else have needs that they want me to hit on today? Okay, because there's a lot of content. I will skip some things. You can just look at the slides later. I mean, at some point I realized with these 8:30 tutorials, and I was nodding out yesterday in the tutorial I was in. So I don't want to cover too much content. But I want you to get the key ideas. Okay, so when I was doing my PhD, I had these symbolic relational techniques, and I didn't think at all about where I'd apply them. I just thought, hey, I've got this great technique. I'm going to make it work. And then at some point I had to publish. And I said, okay, now I need to actually evaluate and compare to other planners. Did I make up 8 domains that interested me? No. I went to the planning competition, and I said, okay, well, there are already planners who evaluate on the planning competition domains. I'm going to use those. Okay. And then, so what you'll find is that these planning competitions are not these benign things that people forget about. They actually direct 5+ years of research. And that's certainly true in the probabilistic planning community. Probabilistic PDDL drove probabilistic planning through 2011, right? All the planners were related to the domains that you could express there. So that's great, but my observation was, and I'll show you for example domains like traffic, you can't express all domains easily or at all in probabilistic PDDL. So it was inherently restricting people's view of probabilistic planning. So my first observation is that these languages direct 5+ years of research, so you want to have expressive enough language to represent the problems that you care about. And for me, you'll see throughout this talk that traffic is a problem that I've cared about, and that's largely driven the constructs that I need for riddle. Okay, so these have driven many years of research. Okay, it's hard to design domains. So of course we all use existing benchmarks. You need to compare. That's why we use them. Unfortunately, our field doesn't yet release planner code. You release all your code, and I really appreciate that. It's certainly helped the field, but not everyone else is in this habit yet, especially in the probabilistic side. I guess on the deterministic side, there is a requirement of release, but on the probabilistic side, it's not been as good. Okay, and so if people don't release their code, then the only way you can compare is on the benchmarks. So it's not surprising that people focus on them. Okay. Okay, so we should choose our languages and problems well if these competitions are so important. Okay, so our current stochastic domain language prior to riddle was probabilistic PDDL. So here's a simple example. What's the, I'm going to assume people here are familiar with PDDL, so what's the thing that probabilistic PDDL adds? Is this probabilistic effect here, right? This effect happens with 0.9 probability, and with 0.1 probability, it doesn't happen. Okay, so in the planning competition up to 2008, there were blocks world and colored blocks world and exploding blocks world and moving stacks blocks world. These competitions, I noticed from my own experience, the competition's got to run next week. You need domains. First thing you do is adapt the existing domain, right? Make it interesting. And I will never claim these problems aren't hard or aren't interesting. But I can tell you from my own time on the job market that it's very hard to give talks about these problems and really engage your audience, right? You should talk about moving containers in ports, right, as opposed to blocks world, same problem. But it does interest people a bit more. So perhaps we should be better at naming. But I guess my claim is there wasn't a whole lot of innovation in the probabilistic domains for the probabilistic competition. And it's largely, as you'll see, due to a huge restriction that you have when you extend PDDL to the probabilistic case. OK. So here's another domain. It's a logistics world. You've got cities, boxes, planes. You want to get certain boxes in certain cities. So we just take our standard probabilistic, our standard PDL domain, and we can make any of these effects stochastic happen with some probability. OK. So we can define large domains as PDL allows us to do, but when you're in the stochastic setting, you don't have concurrency, right? In the deterministic setting, you get concurrency because you say if actions don't conflict, right, you're allowed to execute them concurrently. Okay. However, in the stochastic domain, if you have tons of probabilistic effects, right, can you guarantee that actions don't conflict? That's very hard, especially if lots of things are changing. So inherently, probabilistic PDL has always been restricted to non-concurrent domains for this reason. And so in logistics, it doesn't really make sense to just move one box at a time, right? This doesn't interest really anyone. Okay, so what stochastic problems should we care about? So I'm just looking through the literature. Mars rover is sort of an interesting domain. It's continuous. You have time, robot position, sun angle. It's partially observable, right? And it's even worse, it may be high dimensional partially observable, depending on how you represent your sensors. A lot of stochasticity here. Are you going to achieve your ability to move to an next position, et cetera? Elevator control, particularly annoying problem because lots of things are changing even though you're not changing them. So you're controlling a bank of elevators, right? You have random integer or plus sign arrivals at all the floors, right? And you have a distribution over their destinations. Typically, people on the top floors are going down to the lobby, but people on the bottom floors could go at different points in the building. And at different times of day, you get different distributions. But it's a highly exogenous stochastic process. And so it's critical to model that. The objective in elevator control is not so obvious all the time, right? You could minimize some of the wait times or some of the squared wait times to try to reduce the tail. But it's not just a clear goal-oriented problem. And you may have policy constraints. It's something actually Riddle can handle this, but just to point it out, people might get annoyed if the elevator reverses direction, right? So you want such constraints. Okay, so traffic control. Anyone recognize this city? I'm told it was Brazil. Not sure. But yeah, so traffic is a problem for a lot of us. Okay, does anyone recognize this? Londoners. Oh, this is a sculpture in your city. It's not a real traffic light. It's a sculpture. Okay, so traffic is concurrent and independent exogenous events, right? This is a problem you just absolutely cannot model in probabilistic PDDL because it just doesn't give you the power to do it. You've got traffic arriving at all edges of your network, moving stochastically internally. Even if you don't, there is no such thing as a no-op. You're always doing something in traffic. The lights are always taking some setting. And it's concurrent. This is a problem where, you might have two lanes merging into a single lane, right? And you've got to handle that sort of stochastic conflict. What are cars going to do? As I model it, and a lot of people in the literature model, it's continuous. You have density and density and velocity per segment, and these are nonlinear. The relationship between velocity and density is a nonlinear relationship. It's also partially observable because you only, in practice, observe the inductive loops of the stop lines, right? You've got now some cities are very good now about putting cameras on their lights. It's a very controlled vision problem where they can actually pick up the queue lengths, whether it's buses and so on. But for the most part, most existing control only gives you an inductive loop that tells you, is there a car at the stop line, right? So heavily partially observed. Okay, so this is certainly a problem you cannot model in PDDL. Okay. So if you look at what happened with the probabilistic languages, so let's start from the beginning. So with strips, we know the progression, ADL, PDDL, PDDL, right? So we got more expressive over time. At some point in 2004, probabilistic PDL split off, and it was the first, I think, good attempt to get stochasticity into PDDL domains. But the nice thing about PDDL is it kept on evolving, right? As people needed more expressivity, the language evolved. 3.0, is there 4.0 now for PDDL? I swear I heard it PDDL 4.0. Okay, but 3.2. Okay. So probabilistic PDDL sort of remained stagnant, but still in 2010 people were publishing on it, right? And for me this was, people had pretty well explored it, but we needed to move on because we couldn't model a lot of interesting problems. Okay. So I'm going to come back to this. My claim is that PDDL sort of probabilistic PDDL branched off the wrong direction here. So I'll come back to the slide. Because probabilistically, so in the classical setting, you know exactly what's going to happen, right? You know when things conflict and they don't. When you have lots of independent stochastic effects, lots of things, a truck goes to pick up a box, but the box may or may not be there, right? When you have tons of stochastic things, there's always going to be some small probability that there was a conflict. So okay. So I see your point. There are some as long as you can guarantee there were no conflicts, as long as you can guarantee there's probability 0 of a conflict, then you could extend that concurrency semantics to probabilistic PDDL. Yeah, fair enough. But other domains you're going to see it's basically impossible. Okay. So let's look at traffic control. So this is kind of a fun problem. This is, I just came out of NICT in Australia, and we worked with the traffic folks there. And we have tons of great data for traffic. This is kind of fun. You can see a week in the life of Sydney. Monday, Tuesday, Wednesday, you wake up. Thursday, Friday, red is high traffic. And Friday. Saturday, weekends a bit later, Saturday, and then Sunday. Okay, so we have tons of data, right? And we want to turn these data into models, and we want to do control in models. So just recently, I had a student manage to actually solve this traffic control problem. Right? This is pretty impressive. He's solving this with a mixed integer linear program. And he can actually solve for the optimal control in this network given the learned model, which is pretty impressive. So you can sort of see queues backing up here and then draining. What's that? Okay, assume green is good and red's bad. So green is an empty network. I can play it again. So whenever you see red, you've got traffic queuing. Try again. So you can actually see the queues building up here, light traffic yellow, and then some red queues. So from some high density traffic here. It's all trying to drain. Okay. But you've got these sort of highly exogenous stochastic models, right? You want to do control in these models, and we want to model problems like this and do control in them. Okay. So first thing, I would like unrestricted concurrency. So in probabilistic PDDL, you'd have to enumerate joint actions in PDDL and ensure they don't conflict with any probability. In PDDL 2.1, you got to, it's deterministic, so you got to execute anything that didn't conflict. But again, when you're stochastic, some things will almost always conflict in most domains. So I would claim for the probabilistic setting you need unrestricted concurrency, right? You actually need to resolve the effects of conflicts when they do occur, as opposed to just say you can't do that. Okay. So for traffic, you need multiple independent exogenous events, all the arrivals at the edges of the network. You know, the problem with probably PDL is that you only allow sort of one independent event to affect the fluent, right? And that's sort of, you know, for traffic, too many things. All the roads that come into another road, right, can affect that next road, right? And you've got to resolve those conflicts again, especially when they're independent. Okay. Okay. So what I realized sort of is that we need something more like a relational dynamic Bayes network to ensure that we always have a very clear transition model given the previous state. Okay. So going on to more things that are missing in probabilistic PDL. Probabilistic PDL basically only had this discrete probabilistic effect. 0.9 probability this happens, 0.1 probability this happens, right? But we want sort of very expressive models. I mean, difference equations that are stochastic. We want, okay, I don't have, you know, so we want Poisson and all sort of our standard list of distributions. We want that in traffic and we want partial observability. Again, we only represent the stop line for traffic control. Okay, so more things missing in probabilistic PDL. This is actually things that I found difficult when I competed in the 2006 competition. So I worked on lifted planning for my thesis, and a problem I have is that in PDDL, when you have fluents for traffic network topology, how are roads connected to each other, and you have fluents for properties of roads. Is there a truck on it, right? Some things are changing, like is the truck on a road, and some things like the topology typically aren't changing. And the problem is if you have a lifted planner, you inherently have to plan assuming that everything changes, right? So when I did my lifted planner in 2006, you know, the policy initially would say, well, if this road's connected to this road, or there's some path, right? And you see this long logical formula saying these 2 points are connected. But the fact of the matter is, once I had a planning instance, I knew what the road topology was. So in 2006, I had to actually encode axioms to say these things don't change. And this upset the organizers a bit, but it's the only way that I could run my planner. But I mean, based on this experience now, I think it's critical to differentiate fluents from non-fluents, things that change versus things that don't change. So especially lifted planners that try to generalize know that they don't have to reason about things changing like traffic network topology. Okay. Okay. Yeah, that's true. Okay. So for that, I could have done it. There's another thing for blocks world. So well, okay. So when I get to state invariance, I'll mention another reason that I needed axioms, or sort of things to say that things weren't changing. Okay. So you need expressive rewards and probabilities. So sums, products, nonlinear functions, ratios, conditionals, right? I didn't want to restrict what you could represent as a reward. So when you have joint actions, so what you notice in Riddle is that there are no preconditions for an action, right? I have a separate section defining axioms for what actions are jointly executable and which actions aren't. They're just literally axioms. Okay, so you could say things, for example, that two traffic lights cannot go into a given state because this would be a conflicting sort of crossing traffic pattern that you don't allow. But more critically, and again, this is a problem for lifted planners. So in logistics world in 2006, no one ever said you can't have a vehicle in two different locations, right? So I actually had to axiomize this. Otherwise, my planner said, you know, if vehicles in 2 locations or 3 locations or 4 locations, do these things. So sort of, in addition to these non-fluents which help lifted planners, I also want state invariance that sort of axiomize things that are possible and impossible. And again, if you're doing regression planning, you need to prune out all these states that you regress that are impossible. Okay. So these aren't critical. You can put these in probabilistic PDDL, but I think you need them in general in planning languages. Okay. So if we want to model lazy domains that we want to model, how do we do it? And I claim actually we need to borrow from the MDP and POMDP community. So here is my ICAPS evolution of languages, right? So what happened is that in the UAI community, they started with dynamic Bayes nets in '89, a very expressive representation for transition distributions. But these were propositional, right? And then some more structured propositional problems came along. And finally, when I created Riddle, I said I'm going to try to take the best of PDDL and the lifted relational representation. I'm going to combine that with dynamic Bayes nets, effectively getting a relational dynamic Bayes net. Okay, so that's where the acronym Riddle comes from. It's a relational dynamical influence diagram. So an influence diagram is a generalization of a Bayes net where you add actions and rewards. So relational dynamic influence diagram language. So who knows what a Bayes net is? Okay. Bayes net? Yeah, okay, good. Okay. So is there anyone who's okay. So I mean, this is basically what Riddle compiles to. How it's represented. You have state variables x1, x2. You have next state variables x1 prime, x2 prime. You have conditional probabilities. The probability of x1 prime given x1 was probability of x2 prime given what? Given x1 and x2. Okay. So this is your state evolution. Now the actions can influence that state evolution. Sorry, it's actually the probability of x1 prime given x1 and the action A. Okay. So you might have observations here. That's probability of O1 given x2 and so on. And you have reward as a function of certain state variables. Okay. So basically, Riddle is just a lifted specification for a dynamical Bayes net. And all I need to do, the only thing I need to do once I've defined my fluence is define what the transition distribution is, the probability of next state variables given the previous state variables, and what the reward function is as a function of the state variables or the state fluence. Okay? So for those from the UAI community, probably not here, it's very related to these previous formalisms called Spud and symbolic Perseus, so this is relational. Okay, so I mean, I think it should be obvious that we can all define fluence. That's pretty trivial. The question is, how do we define these distributions? That's the key difference between probabilistic PDDL and Riddle, is how you define the distributions. Okay, so I'm going to give you an example from this domain, which is Wildfire. So because it's sort of a very intuitive domain. Okay, so we have cells here. We have a grid of 4 by 10 cells. We're watching a wildfire spread. So red is I think ignition of a fire. I believe brown is burning. Brown is when you've removed fuel from an area, so it can't burn. Of course, you can't remove fuel from areas with the target area is T with housing because the fuel is the house itself. Okay. So a fire is burning. You can remove fuel to sort of create a fire break. But if the fire burns, eventually the cell goes to black and it won't burn again. Okay. So the question is, given limited resources, maybe 3 fire brigades, how do you distribute them to create fire breaks, to put out fires in order to sort of save the most number of target cells? Okay. So fires spread from nearby cells to each other. No, let's try it again. Okay, so you'll see the fire spread, and yeah, eventually. Okay, sorry, I think black here is actually cut out and brown is actually burned. What I'm saying. Okay, so we burned a lot of our target cells here. Okay, so I think people get the basic intuition that you have this fire that's spreading in the grid. Okay, and I bring this up because I think if you get a sense of the domain, it's easy to see what's happening in Riddle here. Now this turned out a bit smaller than I liked it. Marie, can you read this? Okay. So I hope your vision's good. Okay, so what do we have? We have cells on an XY grid, right? And we have 2 properties of cells on an XY grid. They're either burning, true or false, and they're out of fuel, true or false. Okay, there are actions which are put out the fire at cell XY, and we should have cutout. Yeah, I don't know what cutout's not here. Okay, so cutout is to remove fuel. I think I dropped that from this description. Okay, so we want to say in a next state, how are cells burning as a function of the previous state? Okay. Well, if you put out the fire in that cell XY, right, then it can't be burning. Then the burning is false. Okay. However, if you didn't put out the fire in the cell, and the cell's not out of fuel, and the cell's not burning, then it might ignite. And what's the probability of ignition? Well, it's a draw from a Bernoulli random variable. It's a coin flip. What's the probability of the coin flip being true or false? It's a sigmoidal function of how many of your neighbors are burning over the number of neighbors, right? So I think once you exceed 4.5 neighbors here, you have a very high chance of being on fire. So if this is just a sigmoidal exponential function. But you'll see things like the ability to sum over all x2 and y2 such that x2 and y2 are a neighbor of x and y, and they're burning. So you can actually do counting. Okay? So does everyone see what's going on here? Okay? So I'm saying the probability according to the number of neighbors that are burning, right? And if all the previous conditions didn't hold and I fall into this branch, then I just maintain the last. Then the burning prime is just equal to burning in the previous state. Okay. So for out of fuel, it's a little bit easier. Is the cell out of fuel? Well, it's either out of fuel if it was already out of fuel or if it was burning, right? Because once it's burning, we know it's going to be out of fuel in the next stage. Okay. So the key thing here, unlike PDDL, which specifies effects of actions, right? Now my actions are just variables, like everything else, and I'm really focusing on defining the next state distribution, almost as a simulator, as a set of sampling instructions. Let me just go back to this. Yeah, right. So again, for every next state variable, I'm specifying the conditional probability, right, as sampling instructions. So this is what we call a probabilistic program. It's a very imperative view of sampling. We can actually convert this to a proper distribution. Yep.
So are you saying that analysis of that Bernoulli function is what spurs you to do the put-out action, or are you saying you just put out randomly, and then it will happen to be the case that the fire propagates by that particular probability that you've got? I mean, how do you make an intelligent strategy to put out the fire in particular cells because you know that that's how it will spread?
But isn't it the job of the planner? I mean, I don't. It's a question regarding.
No, sorry, I'm not asking you to solve it. I just mean, is it the expectation that the planner will, or your planner, let's take as an example, will choose where to put out by understanding how that probability works? So if I replace that Bernoulli function with some other function, then you get different behavior.
Okay.
Never mind, we can discuss it later.
Sorry. I mean, I'm just. No, I think when you see, so the brown cells are burned here, and the black cells are ones where you've cut out. So in some cases, the fires have been put out. I don't know why PowerPoint can't.
Those are actually plan executions that you're showing here, right?
Yeah, now this is going to be a random plan execution.
Random plan.
Yeah. No, this is just, it was just meant to show the evolution of the system. Okay, but all I'm doing here, Maria, is just specifying the transition dynamics, right? I'm going to let the planner figure. Okay. As to what's actually going on in the domain, or okay. Okay. So this is the transition. So the only thing once I specified the fluents, burning, out of fuel, put out action fluents, and so on, is I need to specify the reward, right? And in Wildfire, there's some. I'm just going to sum over all the cells where I've cut out fuel. And I'm going to penalize them according to the cost of cutout. I'm going to sum over all cells where I've put out a fire, right? That's expensive, it requires the fire brigade, and the cost of put out, and so on. So I just want to sum a bunch of things according to the costs of applying them. And that this is inherently concurrent, right? I can cut out or put out as many cells as I want, and the thing still sort of evolves stochastically given those actions. Okay, so the key thing is that I'm going to specify these transition semantics as probabilistic programs, assembly instructions, but most planners, aside from the UCT planners, don't want to use a simulator directly. This is easy to simulate, right? If I want to sample the value of a live, I just go through the instructions, and if I hit a random variable, I sample from it. Otherwise, it's a completely procedural execution. Okay. So sampling from it in forward sampling is fairly easy, but what most planners need is to actually compile this representation into a dynamic Bayes net, right? Previous state variables are ovals, next state variables are ovals, actions are these rectangles, right? And most of the probabilistic planners actually take a dynamic Bayes net or a dynamical influence diagram as input. And so what the Riddle software does is it takes in the probabilistic program and it automatically translates to these inputs required by the other planners. So the key thing for me when I was specifying traffic initially is that I was trying to specify these dBns directly. And if you look at this, like this we'll see later is the game of life. It has fairly simple rules about how patterns spread in the game of life. It's amazingly painful to actually write down the direct dBn and the distributions. Whenever I did this, even programmatically, I always made mistakes. It's much easier to write this very high-level program that you can simulate and sort of verify that it simulates correctly, and then compile it into this formalism. So this was my original motivation for defining Riddle. I needed dBns, but a more error-free way of specifying them. Okay. So what you'll notice in Riddle is that everything's a fluent. The states are fluents, the actions are fluents, the observations are fluents. Right? I don't distinguish inherently between actions and state fluents, except that the state fluents evolve stochastically, the action fluents are set by the planner. Okay, so everything's a fluent. If you want correlated effects in dBns, you're going to need intermediate fluents, which are fluents that live between the current state and the next state. But everything's a fluent. So, for example, you can do derived predicates with intermediate fluents. Okay, and then you have lots of constant non-fluents for all the topology relations and so on, things that don't change. Okay, so what the fluents can be binary, they can be multi-valued or enumerated, they can be integer and continuous. And as of Riddle 2, which I'm developing with Thomas Keller, we can have object fluents. So if it's a type, you can now use it in Riddle. Okay, so again, the semantics, you specify this probabilistic program, but the semantics is a ground dBn or influence diagram. And what I want to claim is that this gives you an unambiguous specification of the transition semantics, right? If things conflict, the sampling instructions tell you how to sample. Right, is that clear? So in PDDL, you could have two actions with conflicting effects, right? that'll never happen in riddle. Because if I want to sample a next state, I'm just executing this program and sampling, right? I always get one fixed outcome unambiguously, and that corresponds to a distribution. So I think there is strong justification for this sort of next state fluent focused transitions when you have concurrency and distributions. Okay, this naturally supports independent exogenous events. Okay, so of course you'll notice I general expressions in transition reward, logical expressions, arithmetic expressions. You would have seen the summation. Of course, you can also do products, whatever you want to do, you can do it. Okay. Okay. One thing, if you're reading a riddle, just take note of, if it's a Boolean expression and you use it in an arithmetic expression, true is assumed to be 1 and false is assumed to be 0. This is why I'm summing over binary expressions. Okay. I'm just going to skip over this. I don't think it's critical. Okay, let's go over the B and F grammar in infinite tedium.
We want you to go back to slide.
No, I was joking. Okay. Yep.
So, sorry, do you mind if I just ask you?
Please. I'd rather have an interactive talk so people stay awake.
So the thing I was asking earlier, a better way to ask it maybe is, in the DBNs that you generate from the RDDL, the action nodes are always the root nodes of the DBNs, right? Or do they sometimes do action nodes sometimes? See, what it seems to me is that the action put out fire, for example, doesn't have a precondition, so that you apply the action, you then propagate the effect according to your model, but then you just apply another action. What's the causal information connecting action so that you can choose to apply this action because previously you applied it and it had a certain effect?
Okay, there's something fundamental.
Yeah.
Okay, a critical misunderstanding, and I don't.
Can you clarify it? I mean, what am I missing?
So here's a DBN. We agreed that if I had values of all the state variables, which are these blue ovals, and if I had assigned values to all of my action variables, then I could sample the next state. So the next state conditions on both the actions and the previous state. So if this is burning, I don't know what it is, but if it was burning of cell x1, y1, right, and this was put out x1, y1, right, then it won't be burning in the next state.
So am I right in saying that this is just the description of the effect of the action, not its precondition? Because
But there are no preconditions in riddle at all.
Exactly.
but you just said you can model them through state invariants.
Yeah, so you can restrict what legal actions the planner is allowed to execute through the global action preconditions, right? So you can say for traffic, don't ever set these two lights in this configuration.
Yeah, okay, so you don't call it a precondition, but you can model this kind of thing through this kind of state invariant.
Yeah, exactly. And I felt for joint concurrent actions, it was it's hard to say for a given action what are all of the other things that other actions can't do, right? It was easier to pull out all the constraints for what actions were executable into just a joint section that said here are axioms saying what you can and cannot do. It seemed cleaner to me.
Well, you're making lots of departures from the PDDL setting
For sure.
that are not absolutely necessary, perhaps.
But it's, when you're stochastic, I think you've got to, right? I don't think you can even start to model traffic in a deterministic setting because it's not deterministic. But maybe you could assume sort of transitions and fixed inputs.
Well, I mean, you could sort of explicate about a special case where an action has a particular precondition, like the truck has to be in A in order to drive from A to B. I mean, sort of to us, it's like the most natural thing in the world. So it's a bit disturbing that you depart from this completely.
But I really, so it requires you for traffic. Yeah, I don't know.
Can I say something?
Yeah.
It seems to me that actually there is no departure here from PDDL because when you have a conditional distribution CDT for variables on the
yeah, if you want to allow an action to just lead to a no-op, right? I mean, so you get all conditional effects. So in
I could say here that if the target is not in the right position, nothing's going to happen.
yeah.
But I cannot say if the target is not in the right position, I can't apply the action at all. That's not something I say in this part of the formalism. I mean, this is really not a big criticism. I'm just saying, I mean, you make lots of choices, and from the perspective, they're probably very natural. Because it creates a bit of a community clash because they're completely opposite to what I'm used to.
Yeah, but I think anything you want to say in preconditions in PDDL, I think you can say in riddle, right? It's just
I'm completely sure of that. I mean, you don't lose the explicit. You can just put the pieces in different places.
yeah. But I think when you get to joint action conflicts, I just think it's cleaner to have everything separate.
That is the point you could also make in classicism, right? It's not specific to the probabilistic set.
I think effects-based semantics makes a lot of sense for deterministic settings. It's very clean, very clear. I think when you, what I realized is that the action effects-based semantics don't allow you to resolve the conflicts of all these randomly executing processes. Whereas pointing out that basically whenever you execute this, you unambiguously sample, right, a fixed sample no matter how things conflicted. So I think it comes down to the fact that you need more of this fluent focused transition semantics as opposed to an action focused transition semantics. And as I pointed out earlier, the MDP community had been doing this since '89, right? It's just that when people did the probabilistic competition, they chose to branch off PDDL as opposed to the DBN paradigm. And so what I will say is that people email me and they say sometimes, this is Riddle's amazing for compactly modeling certain problems, and then I get other emails from people saying, man, I tried to translate this PDDL domain to this sort of this fluent-based semantics, and it's horrible. And so, for example, if you look at Triangle Tire World in the 2014 competition, in the domain description, in the comments, I give this very compact PDDL description, maybe like 5 or 6 lines, and then I give this horribly annoying, probabilistic program description for Riddle. So things that are heavily action effects based, when there's a strong frame assumption saying the only thing that changes is what was changed by the action, then PDDL is very natural. When things are heavily stochastic, everything's changing around you no matter what you do, I find that this sort of DBN is much more natural.
It's really like primary difference here, like all of those things happen exogenously.
Yeah. So when you have a strong frame assumption, the only things affected by the action change stochastically, then probably PDDL is the language you want. But it just ignores so many domains that you can't model. Okay, so I want to skip all these bullet point slides because they get boring. Okay, so I can go through some examples to give you a bit more of the idea of the syntax of Riddle. Let me go through one, and then after this, I'll let you ask if you want to go through more. This will be short. So here's the simplest Riddle domain that I can come up with. It's not lifted at all. It's completely propositional. I have propositions Q, R, and P. They're Boolean. I have an action that's Boolean. Next state variables and reward. Okay. So for example, the probability of P prime given P and R could be given by this table. Okay. So I want to specify this as Riddle. So you have this P variable section. Why is it called P variable? It was for parameterized variables because later for like burning, we'll give burning parameters of X and Y for this cell position. But right now we're not lifting, so we just have P, Q, R. These are state fluents. The action, A is an action fluent. They're all Boolean. Defaults just help in compact communication between the client and server. Okay, so conditional probability functions, CPFs. So, right, remember here was my transition probability for probability P prime given the previous state of P and R. Right, I'm not going to write it as a stochastic program. So I say, to evaluate whether P prime is true or false, I say if P and R is true, then I sample from Bernoulli with 0.9, I'll sample from Bernoulli with 0.3. So Q prime is very much similar, just a bit more structure. R prime, so you'll see cron deltas a lot in the code. So the thing is, when you have a stochastic transition that is actually deterministic, you want to place all the probability mass on one outcome. So this says, if Q is false, then R prime takes the value of R. Place all the probability mass on the transition at the current value of R. Otherwise, take the value of this by implication, right, whether it's true or false, and assign that to R prime. Okay. Again, remember that the reward, Boolean variables are interpreted as 0 or 1 values when they're in arithmetic expressions. Okay? So it's a very simple riddle domain. Goes by p variable, CPFs, and reward. Okay. So you can also have things like intermediate variables, right, that may help generate things like observations, right? And so they may be integer or multivalued or continuous, right? And so now I have some more variables, again, P, Q, and R, which are Boolean. Now I have I1 and I2. I1 is an int. I2 is an enum. The enum values are defined up here at low, at medium, at high. O1 and O2 are observations. This is a partially observed domain. One's Boolean, one's real. And my action is still Boolean. So these were the same transitions for P, Q, and R as showed previously. Let's look at I1 and I2. So now I1 was an integer. And we're going to place all the probabilities. So what's I1 in the next state? Well, it's simply whatever the sum of P, Q, and R is, right? So I'm going to place all the probability mass on whatever this value is. I2 was an enum, so I have a discrete distribution. So I2 takes value at low with this probability, at medium with this probability, and at high with this probability. And we've now added in otherwise just to sort of help make everything sum to 1 easily. But if you do all the math here, this does sum to 1 properly. Note that the arguments, say for O1, which is Boolean, remember the arguments of Bernoulli's can be any expression. They can even be other random variables. You can just nest these things arbitrarily. It's just a program that you sort of execute and evaluate from the inside out, right? So if P, Q, and R are all true, then you get probability 1. If they're all false, you get probability 0. Okay, finally, for O2, it's a continuous variable. To determine the transition, I'm going to switch on I2, which was an enum. If I2 was of the low value, then the value of O2 in the next state is the value of I1 plus 1.0 plus a sample from a normal distribution where the variance depends on the square of I1, right? So here I'm adding in some Gaussian noise with some state-dependent variance. Okay. So a lot. Yeah.
Does this take up the probabilistic program? Like that? I mean, like you had if and switch, obviously, right?
Yeah.
That's probably it.
Oh, sorry. Okay, we went.
No.
You can hear him, but
Yeah, sorry. I'm not paying attention. Poor viewers at home. Sorry, guys. Okay, sorry, Georg.
So the program language basically allows if and switch, like it's basically if statements only, right?
For the deterministic control flow, yeah. So there's no fors, right? If that's what you're asking. You can do in riddle 2 you can do tail recursion, as long as you don't self-refer, because I can compile out all the conditionals in the DBN. But that's riddle 2. So you can do some effects of for loops. But I think for a lot of people, the only question they get when they execute this is, what the heck do you do when you hit these distributions? And the idea is that you sample, right? Okay. So I'm not going to do game of life. It's a fun domain to specify, but if you understood Wildfire, this is just sort of another grid-based version of Wildfire, so I'm not going to do this one. But the slides are online if you want to look at it. But I'll tell you, my motivation here was, if people know the game of life, it's a cellular automaton. There was a question back in the 70s as to whether there were patterns that persisted indefinitely. And the answer is affirmative. Here are some patterns. And my idea was, can we actually allow a planner to intervene and try to maintain as many cells that are alive as possible? So can we let God intervene and help the life here? So that was it was apparently a very a very difficult domain in the IPC 2011. Everyone complained about how hard it was to solve this because it was stochastic. And when I complained about, so I think my favorite story is that when I was giving the IPC 2011 presentation and I complained that blocks world was sort of a problem that was a bit toy and not generating a whole lot of interest in planning, Alan Fern said, but you had Game of Life and in your competition, how is that interesting? It's a fair question. It's fun though. Okay. Right, so one thing that you'll simply notice in Game of Life here is that I have, in the instance, I have non-fluents, and all these things are known by planners not to change. Okay. So if I have one instance, right, of Game of Life with this topology of the neighbors and this many cells, I generate this DBN. If I have 3 by 3 cells and this neighborhood relationship, then I generate this DBN. And again, the compiler does this automatically. In the discrete case, the compiler sort of will always work. Here's a question for the audience. In the continuous case, can I always compile these DBNs? So if I sample from a uniform variable, and then I sample from a Gaussian, I add them together, and I cube that, what's the distribution of that random variable, right? I had an imperative way of specifying it, right? But what is it? So when you compile continuous distributions, you get into the algebra of random variables. Requires lots of integrals you can't always evaluate. And so in general, for the general case of the continuous case, I don't have a translator yet for this. And I'm still deciding what the heck to do, given that I can't give exact translations. I mean,
So for some distributions you can, right? Like the variables are Gaussian distributed.
Sure. So for a small subset, I can do that. But that's the problem. I mean, riddle is quite expressive, right? That subset's most often not what you're going to encounter. But yeah, if you want to do a Kalman filter style problem with just Gaussians, then yes, that would compile into a DBN. Okay. This is more or less like Wildfire because it has a complex transition distribution. I'm not going to cover this. So okay, here's a very simple Mars rover problem. Here's a continuous domain. I've got a rover. It's trying to during the daylight time on a Martian day, it's trying to take pictures of points 1, 2, and 3, and has to sort of plan a schedule to do this. Movements and times to take pictures. And the thing is, in the most general case, you would only want certain pictures perhaps taken at certain times a day, depending on the light that's expected. Okay? So your actions are sort of to move in the x and y directions. You might try to hit this corner, and then hit this corner, which hits both picture points 2 and 3, sort of as the minimal amount of movement. So that's what the planner would do, but let's just specify what the domain semantics are. Okay, so we have a bunch of parameterized variables. So as we start with a lot of non-fluents. So what are the x and y positions of pictures? What's the value of taking that picture, right? So different pictures might have different values for the scientific planners. And how far off of the center are we going to allow you to be from the center of a picture point and still allow it to be a valid picture? So a bunch of constants regarding to the pictures that we want to take. For the rover itself, we're going to have 3 variables, x position, y position, and time. So you can do, it's a bit of a hack, you can do continuous time and riddle if you have a single agent, right? Because you can always compute the timeline of that agent. You simply can't mix concurrency and time if you want time in a state like this. So time is a real fluent, x position and y position are also real. So three-dimensional state space. And our actions, we've cleaned this up in riddle 2. In riddle 1, you had to factor out all the parts of an action. So the distance you move in the x direction is real, the distance you move in the y direction is real, and whether you snap a picture is Boolean, true or false. Okay, so these are all the fluents that I need for the state fluents and the action fluents, and all the non-fluent constants. Okay. So how does the rover move? Well, okay, I move according to the distance moved plus some sample from some white noise that scales with how far I've moved. So the farther I move, the more noise, the more variance that I get in my random sample. Same for y as well. In riddle 2, we've added some vectors to make this sort of more natural to specify. How does time evolve? Well, if you snap a picture, we assume that time always advances by 0.25. So place all the probability mass at the value of time plus 0.25. That's the Dirac delta. So if you have discrete values, you need to use Cron delta. Continuous values, you use Dirac delta. However, if you didn't snap a picture, right, and you just moved, right, then we're going to say that the time advances according to how far you've moved. Now, technically, you should probably take Euclidean distance here, and just in riddle 2, we now have square roots and squares and all the arithmetic functions. So in riddle 2, you could now actually have proper Euclidean distance. Here, I just sort of did a Manhattan distance hack. Okay. Okay. The reward basically says if you snap a picture and your time is less than the max time before the sun sets, then you simply sum over all the picture points that you were in. So this says, were you in a picture point? And then if you were and you snap a picture, then you get picture value. And so note that if I was in 2 picture points at the same time, because I'm summing, I'd get the value for both. Okay, if that's clear. And so state action constraints, if I snap a picture, then I cannot move in that step, that time step. Okay, so a simple joint action precondition. Okay, so again, the transition distribution stochastic programming. I think people struggle the most about how to convert stochastic programs to distributions. If you know previous, so I mean, I've never, I fear when I submit the Riddle journal publication because I know everyone's going to say, since blog, since eyeball, we've already had this. There's nothing new here. I'm not claiming that Riddle is anything new in terms of the ideas. They've been used for quite a while. I just built up the tool set to interface with planners that we didn't have before. But again, this is a procedural specification of the sampling process. And I think of it as writing a simulator. Right? This is why for traffic and so on, it's easy to write Riddle domains. I'm actually writing a simulator. And I'm letting the compiler do the task of translating it to something that the planners can read in. Right? OK, so I think this point is sort of clear. I'm not going to belabor it with more examples. But here I had a mixture of a uniform and a Gaussian. OK. OK, so just some high-level things to recall about Riddle. And then since I have a little bit of time, I'm going to cover a really cool application of Riddle that I really liked. So everything's a fluent. States, observations, actions, intermediate fluents, which are derived predicates. The non-fluents, the constants. And for me, it's cool because often the constants turn out to be, the non-fluents turn out to be things that from a learning perspective that I want to learn. So Riddle sort of makes a nice interface to the learning side of things where you want to learn the non-fluents. And we have binary, multi-valued, integer, and continuous fluents. And as of Riddle 2, we now have object fluents. So we have all style fluents. OK, right. Again, the semantics of Riddle, at the end of the day, we're specifying a lifted specification of a dynamic Bayes net plus an influence diagram. And again, I just want to drive home this point that sort of gives you an unambiguous way to sample the next state, even when tons of things conflict. Right? Your program says how to resolve those conflicts. Okay, and that allows unrestricted concurrency. Actions that afflict, you'll still allow to execute because you have an unambiguous way to specify the way to sample the next state variable. Okay, and you get very general objectives. I did not allow infinite horizon in Riddle because I've got to simulate it. The way you operate in practice with Riddle, unlike deterministic planning where you give a plan to the server, in Riddle because it's stochastic, you simulate. The server sends you a state, you send back an action, and you simulate. I don't allow infinite horizon because I could never simulate that, right? So inherently, everything's always finite horizon. Okay. And you have these, it's an interesting thing which throws people off about the state action constraints. It's used for 2 different points. One's to encode legal actions, the other is to assert state invariance. A truck can't be in 2 different places at the same time, et cetera. Again, for lifted planners, these things are kind of quite critical. These are also critical actually for just debugging your domain. So they're literally like assertions. And anything that shouldn't happen in your domain, you should put an assertion, and the simulator will throw an exception if you violate them. So it serves use for just debugging domains plus the lifted planners that might want to use these. Okay. So what does the software have? I have a simulator in translations to a Lisp-like format. So I sort of have a very Java-like format, but folks folks who wanted to parse Riddle didn't like that, so I actually translate to a Lisp-like format if you want to write a recursive descent parser. So spun symbolic Perseus, heavily used in the MDP and PubD community. And for some folks who wanted a probabilistic PDDL translation, I do provide that for the Boolean subset. Okay, so it's a client-server interface. We just dump log files as usual. And there's lots of visualization, and this is critical. So there are hooks in the Riddle code to hook up your own visualizations to different domains. So as you're planning in it, you can see what's happening. So for example, here's a Boolean version of traffic. So this is not as cool as the other version that I showed you, which is continuous. But this is one in the competition. I don't know why I can't. Well, it doesn't want to play. Anyways, it's just a cellular automaton. And you can see how the traffic moves as your planner is planning. And for example, Thomas Keller said, "Did you intend that when traffic is at the stop line and the light turns red, the car disappears?" I said, no. That's clearly a bug in the domain. But I mean, the visualizations are quite critical for getting the domains right. And again, this hooks right into the Riddle simulator. So you basically specify how to visualize your different state fluents. Is it going to work either? Yeah, okay. Sorry, this is my elevators domain. You have 2 elevators. They're going up and down. They have people waiting on floors. They go up and down. Again, quite critical for debugging. Okay. So, one thing I want to encourage in Riddle is that people do submit realistic domains. I think this is critical for the planning community. I know as a student, you work on techniques. You don't necessarily work on domains. And then you've got to evaluate. It'd be great if we all had really realistic, exciting domains that we could evaluate on, right? I think it would help the field progress and help make our claims of progress for problems that people care about. So I'm really trying to collect as many realistic domains as possible. I want to run a hybrid competition competition whenever I can get any planners to actually compete in it. And the domains there are quite interesting. I've got traffic. I've got one simple version of a power problem or an electricity generation problem. And I want more. I want these difficult problems that people might care about for real practical applications. So I did mention Riddle 2 briefly. Some things I've added are all the elementary functions, vectors, and you can actually nest vectors to get matrices and tensors and so on if you want. Object fluents are now in Riddle 2. Thomas pointed out that I should actually separate the definition of dry fluents and intermediate fluents because you might actually want your preconditions to rely on derived fluents, whereas the intermediate fluents could be stochastic, so you can't do that. I do now allow stochastic shortest path problems, recursion. So fluents can now self-reference in the program as long as you don't self-refer, because then I can generate a DAG of all the fluent references. Okay, so there have been 2 previous competitions, and if you want to see what I'm trying to do for the continuous one, then just go to my webpage. It's actually still DANU. I haven't moved it yet, and you'll see what I'm doing for the continuous competition here. Okay, so there are tons of ideas for other domains that I want to model. UAVs with partial observability, some hybrid control problems, so at least Kalman filtering with control, but also nonlinear problems. The dynamic systems from other fields, so population dynamics, chemical, biological systems, physical systems, right? These are all things where you can write simulators. If you can write a simulator, therefore you can easily write the riddle domain. So just for fun, I always want to do pinball. I want to plan for pinball. Environmental climate systems. Bayesian modeling. I mean, this is nice. If you have a POMDP, then you're doing Bayesian belief updating when you track the belief state. So you can do things like Bayesian reinforcement learning, and so on. Okay, riddle 3. I haven't finished specification of riddle 2 yet, but what problems have I encountered with riddle that that are still outstanding? There are some domains that are very easy, very nice to specify with effects, that are horrible at specifying riddle, right? And how do I get the best of both worlds? I don't have a clue, but I would like to know that. If you have any ideas, please let me know. Okay. So time processes, so concurrency and time are quite difficult, which is why I only have discrete time and not continuous time. So I'm still trying to figure out how to do that. Okay, so I had this guy, Zhen Yu. He's out of management science at Tongji University in China. And so he's in management science, and he is not a programmer. No offense to you, Zhen Yu. But he really wanted to use, what he sensed was that we could now model interesting problems that I mean, not only with riddle, but PDL as well. We can now model interesting problems, and there are effective solvers. And for riddle, especially from the 2011, 2014 competitions, Thomas Keller has a very effective solver that he's put online. And so he just, as a management science person, he said, I want to look at epidemic control studies, but rather than use these simple solutions where people say just inoculate the family or the neighbors or so on, I actually want to build models and simulate and see what policies work. And the cool thing is that he's not using planners in a way that I thought he'd be using them. So I won't go into details, but if you know epidemic models, it follows this process of you're susceptible, you become exposed, you become infected, and then you recover. And once you recover, you can't infect anyone else. When you are infected, or when you are infected, you can infect others. And when you have a graph, you specify the probability that one node infects the other as basically a noisy OR function of the other nodes. Okay? And we have products in riddle. We can easily do these sorts of distributions in riddle. So you have two actions in inoculation. If someone's susceptible, you can, if they're not infected yet, then you can inoculate them, and you can also quarantine them. So one nice question he had was, how do I set the cost of inoculation versus quarantine? There is a monetary cost to these things, but there's also a huge social cost. I mean, look what happened with Ebola. People came back from West Africa, and they immediately put them into quarantine for a month, right? And then others probably didn't want to go, right? And help out. So that's actually, from a management science perspective, he was interested in saying, if I set the costs in a certain way, what are the policies that arise? So I mean, he's sort of outside of the box of planning, saying, what's the right way to formalize the domain? Okay. And so what he wanted to do is he wanted to model the domain, and he wanted to compare with the competition-winning planner with simple policies. So in epidemic control, you have policies like inoculate the friends or the neighbors, right, if someone gets infected. And so he didn't think people were going to use Thomas Keller's PROS to actually go out and determine plans in the real world. But he wanted to say, how far are the simple policies used by the epidemiology folks, how far from optimal are those from more optimal plans that you could do with planners? If you find a little gap, then you know actually your simple plans are fairly effective. If you find a large gap, then you know there's probably a lot of space for improvement. Furthermore, how do you set the cost for the best trade-off, right? Again, so he's sort of outside the box thinking of how he applies things in practice. Okay. So he set up a network of nodes, and he's done these simulations of infections, right? I'm not sure if process planning here, and I'm not sure what all the colors mean. I think green's good again, and red's bad. But so then he's built a visualization on top of Riddle, so he actually sees as over time he sees how the network gets infected. He can sort of try from the traces. He can try to recover the infective chains. Whoa. Okay, I'm missing a slide here. But the basic idea is he actually goes out and he talks to policymakers and he says, here's what your policy does in this setting, and here's what an optimal policy would do. And he's trying to sort of influence people to change from one fixed policy to another by saying, okay, you currently use this policy of inoculate just the family or the people who live with the person. I say inoculate all the friends, right? And here's visually how the two planners do. So I sort of always viewed planners as something that we would embed in a fixed controller, like a traffic controller, right? And the way that Zhenyu is using planning is quite interesting, where he's visualizing and then going to the policymakers to try to influence their policy. So I just thought that was a very nice application of Riddle. And
So was the proposed policy better than the simple policy?
yes, it is much better, right? So it does. I mean, yeah. So the question is, what's simple enough for the epidemiology folks to implement that comes a bit closer to what Prost is doing? I mean, they don't want a black box policy. They want something that they can understand. But I think these visualizations help them understand the gap in performance. So if anything, I also want to reinforce the importance of visualizing domains, right? It's quite critical when you're trying to explain the value of your work or policies to others. Okay, so anyways, thank you all for coming. And if you have any questions, I'm happy to take them during the break.